of problem or the new kind of approaches to those problems, which we call as satisfiability problem, right? Shodashish, can you please turn on the recording? Okay, it's already there, right? So is my screen visible, the slide visible?
Yes, sir.
Okay, good. So in the last class, what we have done, we have talked about backtracking search for these constant satisfaction problems, and then we tried to talk about a different set of heuristics. And one heuristics that we have started working on is what we call as filtering technique, right? And in that respect, we have talked about a technique which we call as forward checking. And there, what exactly we were doing while we are trying to assign some value to a variable, then we are trying to check what are the status of the unassigned variables, right? So basically, we are keeping trace of what happens if I assign a value to a particular variable, right? And we strike off the values that are not really permissible for the other variables, right? We can extend that, and we have seen that that is good to a certain extent to talk about, say, the satisfaction with respect to two variables. But you see, whenever we change certain value for a variable, that might have effect in the immediate neighbor, and as well as it might have effect in the other variables that are connected to that variable in some way in the constraint graph, right? And that brings us to another heuristics, which we call as arc consistency. So which basically is motivated by the idea of forward checking, but we extend that to say greater than one hop distance. We can think this to be like this. So let us take an example. So first we define what we mean by an arc to be consistent, and what is an arc in our constraint graph. Basically an interaction between two variables, right? So two such variables here in this definition is x and y. And we say that an arc or an edge from x to y is consistent if we find. So what we are doing here, so we have got two variables, x and y. Now let us freeze the values that y can take. So it might be multiple values, but at this point we know that this assignment is okay, right? Now, while we are trying, what we are trying to do here, we are trying to see what values for x will be permissible. So for that, what we'll do, we'll take individual values that are kind of possible instantiation for x, and for all of them, we try to see whether there exists at least one value in y that goes well with this assignment. So that means it does not violate any constraint. So the direction of the particular edge is from x to y, and let us call this to be this to be head and this to be tail, right? So we'll be checking for every value that is that can be a possible assignment for the tail variable. We need to find out whether for that we have one permissible value, at least one permissible value in y, right? If that is so, then we say this arc is consistent. So let us take an example and try to illustrate. So this is a particular state where we have assigned, say, rate to WA, and all the other values for the other variables, they are kind of, we need to check whether they are okay or not, right? Now let us see what is the constraint graph. So the constraint graph is like this. So we have left out, I guess, Tasmania, because that is not connected to any of these variables. So let us keep that aside. Now we have assigned rate to WA. Now I'll try to check whether this edge WA to NT is consistent or not. So we are checking the arc consistency of this particular edge, right? Now, what are the values that are possible for NT? So red, green, and blue. So what we are checking now? We are checking, say, NT to WA. We have frozen WA, right? So our X is NT and Y is WA, right? And we are trying to check this. Now we will take, so these are all instances of X. So first we'll check with red assignment. So let us see if we assign red to NT, whether that assignment goes well or not, right? But you see, if we assign red to NT, there is a constraint violation because they are neighbor to each other. We cannot assign red here. So that means this arc is not consistent. So there is one X for which this constraint is violated. So that's why this is not really consistent. And how do we make it consistent? We need to remove this if you want to make it consistent, right? Now, if you remove this, we have green and blue, and you see that we can assign any value like green and blue to NT to make it consistent with WA, right? So basically, we see that this NT to WA is not consistent. Let us check the other. So Q to WA. Is this R consistent? So can any one of you tell me whether this is consistent or not by this definition?
Yes, sir, consistent.
So why do you say that?
Sir, because there is no direct connection with WA.
Exactly. So there is no connect. So these are not neighbors. So you can assign any value to Q, right? So that means we have for this edge, if we have an hypothetical edge here, so this edge is consistent, right? So if you see the relationship between R consistency and this forward checking, so whether when we are making a new assignment, we are trying to check whether the other assignments are going well with that. If that is not so, we try to delete some values to enforce consistency, right? And that we want to do for the entire network. Now, whenever we talk about entire network, so that is what we call as the R consistency of the whole CSP. So in the earlier slide, we have talked about R consistency of an individual arc, right? But here we are talking about R consistency of the entire CSP problem. And how do we define that? We say that a CSP is consistent if all the arcs are consistent. And what will happen if we make sure that a CSP is R consistent? What will happen? Can anybody tell me? Can anybody guess what will happen? Why we are talking about this consistency of the entire CSP? I hope that you will be coming up with an answer. The last slide, we have talked about the R consistency of an individual node, right? Individual edge. But here I'm talking about the consistency of the entire CSP and how that is defined. This is defined as if all the arcs in the CSP is consistent, then your CSP is consistent. If we have a situation like this, what good will do that for us? Can anybody guess?
Sir, there will be a solution or an assignment that is each variable can be assigned a values.
Exactly. Thank you. So basically, if we make it consistent, then we can have at least one assignment for which this CSP is satisfiable, right? So so let us see. It is a kind of I told that it is a kind of whenever you are making an assignment, you need to relook the other assignments. And whether you are when you are doing other assignments, then it will have effect in the neighbor of that particular node. So we have a kind of snowball effect here. We have this constraint that is being propagated throughout the network, right? And this is in another term also called constraint propagation. Now let us take some examples here and try to see what we mean by constraint propagation. So, so this is a kind of state, intermediate state where we have assigned some values. For example, we have for W and Q, we have got these values, and these are the kind of possible assignments that we can have. So this is the state of the CSP, say maybe an intermediate state, right? Now in this state, we try to check whether this current CSP is consistent or not. So let us now check this edge from say V to NSW. So my question is, if we go by the definition, whether this is arc consistent, this arc is consistent or not. So can anybody check and tell me whether this is consistent or not? So now our X is V and Y is NSW. Should it be consistent? Atin? Hello? Atin, are you there? Shorashish and others, so those who are not responding, can you please mark? So answer can be, well, I did not understand, or maybe some answer. So if someone is not responding, please mark. Sumit? Hello?
Yes, sir.
So can you tell me whether this arc is consistent or not? The whole point of sharing the video lectures a priori is that maybe you can have a look at it, or at least in the class we can discuss these things. Because while you'll be solving these problems, if you don't understand this, I don't know whether you'll be able to solve the problems or not. Utkalika, can you please try to see whether this arc is consistent or not?
Not consistent.
Why do you say that?
Hello.
Because they are like share the same color, they are the neighbors, so that's why they are not consistent.
So let us go back and try to see what is the definition of arc consistent. So for all values of X, we need to find at least one Y value that is consistent, right? So that is the definition. Now let us check. So can you please mute your mic? Yeah, thank you. So let us check for this value. So this is my X, right? Now for this X, do I have one Y for which this is consistent? We have, right? So you can assign blue here. Even though this red and this red is same, but we have another assignment which is in the form of blue. And if we can make that assignment for NSW, then we see that this is consistent, right? So we need to find at least one Y. So that is the reference, right? So that means for this value, we have consistency. For this value, of course, I have consistency. For this value, I have also consistency, because for this value, I can select, say, red, right? So that's why we can say that this arc is consistent, right? So is that idea clear? So look at this definition.
Yes, sir.
Okay. So now we agree that this arc is consistent. Now let us check, say, SA to NSW. So you can easily see that this arc is consistent, because if we have this, so this is your X. So if we have this blue value for X, I can have this NSW to be red, and which is really consistent, right? Now let us check the reverse. So from NSW to SA. So this is one thing that you need to consider, that this constraint graph is an undirected graph. So that means, so if we have an edge like this, we have to check the constraint from X to Y. Also, we have to check the constraint from Y to X. So these are the two edges we have to check for. So we have checked that from SA to NSW it is consistent, but let us check for NSW to SA. Now, if we have, say, red for NSW, we have a consistency, in the form of like assigning blue to SA. That's fine. Now let us check for blue. If we assign blue to NSW, I do not have any consistent assignment, right? So how do we make it consistent? Any idea?
Remove the blue from NSW.
Right. So let us remove blue from NSW. Now there comes the idea. So the idea of constant propagation. Now, as soon as we remove blue from NSW, let us recheck the the edge from V to NSW, right? So you have to recheck it. So now what we have, we do not have blue here, right? Now let us check for red. Now, as we check, select red for V, we do not have a satisfying assignment in NSW. So we do not have blue anymore. So that means our V to NSW becomes inconsistent, right? So you see that in forward checking, we are just happy with assigning or checking the consistency of the neighboring node. But here, as we are making an arc consistent, that might have effect in the other arcs, and there we may lose consistency, right? And that's what the idea of constant propagation is. And that idea is really powerful, and you'll see in the demo that if we do our consistency, we will be able to reach to the solution pretty earlier than forward checking, right? So basically what we are doing, whenever our variable X is losing a value, we will have to check the neighbors of edge, right? And of course, if you do that, our consistency will detect failure before forward checking. And what is the kind of benefit we'll get if we detect failure early? We can prune the search space in a better way, in a larger way, right? So that's what the idea is. Let us quickly go to the algorithm. So here we are, this algorithm is not really solving the CSP, but what it is doing, it is enforcing that your CSPs are consistent, right? And you know that if we have an R consistent CSP, we have already discussed that we'll be able to find a solution. So that part is really trivial, but the crucial part is making a CSP R consistent, and that algorithm, what we call as AC3. So what is the input to this algorithm? The input to this algorithm is a CSP problem. And what we should start with, we basically have to check all the arcs in CSP. If all the arcs in CSP are consistent, then we know that our CSP is consistent. So that's why we are keeping all the arcs in a queue, right? And of course, whenever we say arcs, so if we have an edge like this, we have to introduce this arc as well as this arc in the queue, right? Now, we will pick up one edge from the queue, and while the queue is not empty, we'll keep on checking the edge, right? Now, we will pick up one edge like xi and xj. So this is your edge that you are taking in your probe xj, right? Now, what we'll do, we will try to see whether this arc is consistent, right? And if this is not consistent, we have to remove some values, right? And from where we will be removing the value? From xi or xj. Can anybody tell from where we should be removing the values?
From XI.
Exactly. So this is one thing you need to remember, that we need to always remove from the tail, right? Now, if we have a removal from xi, so that means that arc is not consistent, right? And what is the implication? The implication is, as soon as I remove one value from xi, we might be having, say, another edge like this. And we need to check the consistency of this as well. So we need to relook this edge, even though we have checked it earlier, right? So basically, I'll talk about this later, remove inconsistent values. Now, if we see that there is a case like this, so we try to find out what the neighbors of xi. So let us consider this x case are the neighbors of xi. And we know that there is a possibility that this new edge xi may become inconsistent because of the change in values of xi, right? And that's why we have to put it in the queue, even though it maybe it has been considered earlier, right? Now let us look at the function remove inconsistent value. So this is what this will be doing. This will be exactly doing the thing like this. So for all x, it will check for whether there exists one y or not. If that is not the case, then we say that we have to remove some value from the domain of xi. And you can look at it and see whether this is happening, what I'm telling in this point or not, right? So I guess this is pretty straightforward to check. I'm not going to detail of this. And if you need that, go through the video that I have shared with you earlier. Now, this algorithm has got a running time n squared d cube. Again, I'm not going to explain this because I have already explained this in the video lecture that I have shared with you earlier. If you have any difficulty in understanding that, you may get back to me, right? Now let us go for dim and see the difference between this forward checking and arc consistency. So is my browser visible?
Yes, sir.
Okay, so let us take a complex graph so that we can see the beauty of this arc consistency with respect to forward checking. So we'll be using backtracking. We have not really discussed ordering, so let us keep ordering. And let's first check with forward checking, filter with forward checking. So look at it carefully. So first value will be assigning to this variable. So we have assigned, say, blue. And so as soon as I select blue here, you see the neighboring nodes, as per forward checking, they will not be having blue in their domain. So they have been removed, right? Now let us go forward to assign, say, red to this. We could have assigned, say, green, but let us assign red to it. And as soon as I assign red to it, this becomes only green, right? Now let's say we choose this. So as we choose blue to be here, what values these neighbors are having now? So they will be having either green or red, right? Now let us assign red here. So as we assign red here, this becomes green. Now you see that there is a problem, right? But forward checking does not see that. Forward checking will go on assigning the values, though we see that there is a potential. Yeah. Is there any question? Hello? Hello, Suman. Is there any? Okay. Right. So you see that forward checking does not see that that there is a problem down there, right? Even though that is very apparent to us. So let us see what forward checking does to it. So it assigns a value green to it, then it tries to do all the stuff. Now it assigns value green to it. Now, as soon as it does that, we have no assignment left for this node, right? So as this is not having any assignment, we'll be doing backtracking, right? So we'll keep on doing this. So we'll be having lots of backtracking here, right? So you can play on your own time. So let us skip this and check what our consistency does in this case, right? So we'll keep on doing this. So we'll be selecting blue here. As we select blue here, it will be kind of first step will be similar to forward checking because our consistency idea is built upon on top of forward checking. Now, as we do this, let us assign red here. So we are doing the same thing. As we assign red here, we have green value here. And so as we have green value here, so there is the difference. Now, arc consistency will check whether these arc as we have changed the domain of these variable, so the connected nodes, their domain will also get changed. And you see, as we have green here, there should not be no green here, right? So you see, our consistency can look ahead in a better way than forward checking. And as a result, let us see what will happen. So let us assign blue here. So if we assign blue here, the blue will be gone from here. And as we have red here, this node is constrained to have blue and green. So you can see the difference between forward checking and our consistency. So you see that here I have a percolating effect of the constraint in the network, right? Now you assign green here and blue, red, and see you do not have any clash here. So you do not have to do backtracking at this point, but backtracking is also possible in our consistency, but the backtracking will be less. You see, this is a case of backtracking, but backtracking will be concentrated on a very local region of the search space than forward checking. So that's how we are gaining if we use our consistency than say forward checking. Though our consistency is very good, but it has got some limitations. So after you enforce our consistency in a CSP, there might be three possible situations. One situation is you can have only one solution left, which is very good to have because you know that I have a solution. Now you can have multiple solutions left that is in some way good, but the other way is that it might be having ambiguity which solution to take, right? But again, that is not as bad as we can think of. So one example for this is that if you look at this assignment, we have assigned red to here and we can assign green here. And if you assign green here, I can assign blue here. So this is one solution. The other solution can be say red, blue and green here, right? So you have multiple solutions. Even though, so but the bad case is even though you have defined your network to be consistent, entirely consistent, it might not have any solution. So the particular example is this. So here you can see pairwise this is consistent, right? So pairwise every edge is consistent, but you cannot have a kind of satisfying assignment that will satisfy all the constraints together. So that might also happen to our consistency. Now we have talked about the filtering technique for pruning the search space. Now let us talk about ordering heuristics. Again, that will give us a better way to prune the search space. So the first heuristics that we like to talk about is the minimum remaining value heuristics. So when we talk about ordering, let us try to look back. Whenever we talk about making a decision in CSP, there are two decisions that we are making. One is, first of all, we are choosing the variable for which we have to make the assignment. So which variable? So that is the first question. The second question is, for a chosen variable, what is the value that we are going to choose among multiple values? So if you look at the demo that we have talked about, there we did not really care about which node we are trying to paint first, right? But that has really got a very huge effect in pruning your search space, right? So as per this minimum remaining value or MRV heuristic goes, it says that you choose a variable that has the fewest legal values left in this domain. So can you guess what is the motivation for this? So what are you doing? Let's say we have got n variables which are unassigned, and we want to choose a variable which has got fewest legal values left in its domain. So the question is why this should be a good heuristics. Is there any answer from you? Can you guess? why we're saying this, that this can be a kind of good way to look at the problem. Siddharth? Hello? I don't know. So let me just first check whether this makes sense or not. We are kind of discussing, right? So it might be the answer is yes or not, yes or no.
Yes, sir.
So now if we agree that this is good, then you need to answer why this should be good.
So, sir, we can imagine a 3-node cycle A, B, C. Let us assign some value to A, and B and C are left.
Okay.
Let us imagine C is left with only one value and B is left with maybe 2 or 3.
Exactly.
So either we can select B at this point or C at this point.
Right.
Now let us say that we imagine we select B and we assign some value to B so that C is left with no other value.
Exactly.
Then we have to again backtrack.
Right. Right.
So instead of that, if you were selected C first and assigned, then we would know if a solution is possible or not early.
Exactly. So let me put your words in a different way. So basically, if we choose the variable which has got the least value, so in your case, the variable, it is only having one value left, right? Now, if we choose that variable to be assigned first, so if the solution is to fail, then it will fail early, right? So I do not need to go for multiple assignments, right? So instead, if we would have selected the other variable, so after doing so many assignments, finally we'll say that the choice that the other variable which is having least value is having, that is never going to work. So we want to detect that early, and that's why this particular heuristics is called fail first. So if we have to fail, let us fail first, so that we do not need to waste our time in moving around in the search space unnecessarily, right? So the particular example in this case, so this is the particular scenario where we have assigned rate to WA, and we have two variables NT and SA. We can select any one of them using this MRV. So let us select, say, NT to be assigned with some value. Let us assign, say, green value to it. Now we have, say, SA, and SA is the variable which is having only one value. We'll be using that, and we'll be going on assigning this. So more or less this will work. And the idea is we need to we will just try to see whether we can fail first. I will not say first, fail fast. It should be fail fast. So if we have to fail, we just let us fail fast. Now the other kind of ordering that relates to the values, right? So here in the earlier case, we have chosen the variable that is most constrained. So if we have least number of assignment or possible assignments we are left with, that means that variable is most constrained. But while we are choosing the value, this is opposite. We'll be choosing the value that is least constrained, and that is what we call as LCV. And what does it say? It says that choose a variable that rules out the fewest values in the remaining variable, right? So that it keeps the search space bit open, right? So let us take an example of this to illustrate the idea. So at this point, we have chosen, we have to decide. So we have chosen this variable Q, right, to be assigned. Now Q is left with two values. One is red, another is blue. Now the question is which one to try out first. So there are two contenders. One is either we can have red here or we can have blue here. Now if we have red here, so if we check for say SA, so how this what value it can take? It can take value say blue. So SA is left with blue. But what is the kind of value that SA is left with in this case? Empty, right? So as per this ordering, we'll be using the blue value. Sorry, we will be using the red value than blue value, because we know that if we assign red value to here, it will rule out the fewest values in the neighboring variable or the remaining variable, right? And if we have this kind of situation, it will be able to, if we combine this ordering and filtering, it will be able to solve the n queen problem up to say 1000 value for n equal to 1000, right? So earlier it used to be say 20 or something like that. Now we have achieved a kind of great deal of efficiency, right? Now, I'm not going for the demo. You can play on your own and check how the idea is working. And this is a kind of bit of comparison in for the two problems. One is painting USA and map of USA and NPN problem, right? And as you can see that if we combine this forward checking with MRV, we have really gained a huge number of, so we have less number of comparisons or less number of steps that are involved here, right? Now we can make the solvers more efficient. So let us talk about efficient solvers for CSP. So for that, we will extend the idea of R consistency in form of K consistency, right? So again, if we talk about consistency, consistency is basically no violation of constraints, right? So if we have a CSP that is not violating any constraint, then we say that CSP is consistent. Now this consistency might have degrees associated with it. So let us see what are the degrees that we are talking about. So we have talked about unary constraints. And what are unary constraints? There we are imposing consistency in the node level, right? So basically we are saying that this particular node should be having only this value, or this particular node cannot be having this value. As we are considering only one variable here, for the unary constraints, they are called one consistency, right? So if you are establishing consistency in the node level, so you are establishing one consistency. Now you can easily guess what do we mean by two consistency. By two consistency, we mean R consistency. Basically, we have two variables here and we have an assignment, and we try to see whether that assignment goes well with the assignment in the other node or not. As we are considering two variables here, it is called two consistency, and our consistency is actually our realization of two consistency. And where do we apply it? We apply it in the case where we are solving a binary CSP problem. And we can extend it to further by considering K consistency. And what does that mean? If you have assigned only values to K minus 1 nodes, and you want to check whether the assignment of the K node goes well with the assignment in the K minus 1 node or not, then we say that if we have consistency there, we define this to be K consistent, right? And basically, if we have K consistency, we have K variables associated with this problem, right? Now, we define something called strong K consistency. And what do we mean by that? If we see our CSP is K minus 1 consistent, K minus 2 consistent, and also up to 1 consistent. So in all the levels of variables, it is consistent. Then we say we have a strong consistency in our CSP. And what good that will do for us? So we can claim that if we have inconsistency, strong inconsistency in our CSP, so that means we can have a solution without doing any backtracking. So why we are saying this? Let us see. So what we can do, we can choose any variable and perform a random assignment, right? Now what we are doing here, we are assigning a value to a variable, and that brings us to the domain of checking whether this is one consistent or not. And we have, as we have defined the problem to be inconsistent. And what does that mean? That means this infers, or this implies, that this problem is one consistent. So as this is one consistent, irrespective of what value we choose for that variable, we'll be having always a satisfying assignment. So we do not need to do backtracking. Now choose another variable. Now, as we have defined this to be inconsistent, so that means this is two consistent also. Now, as this is two consistent, whatever choice we make for the next variable, this is consistent with the choice in the first. So that is the definition of two consistency. So we can also extend this by choosing other variable. And at every point we see that we do not need to do backtrack because all the assignments, they are getting consistent, right? But the point is, if we try to enforce inconsistency, then that is as hard as solving the problem or having the solution. So that means though theoretically it is good, but practically, if we want to design an algorithm for this establishing strong inconsistency, that is as hard as solving the problem. And we know that in the worst case, we have an exponential time to solve the problem, this CSP kind of problem, right? So what do? We would hit a middle ground. We do a trade-off between our consistency and three consistencies. For example, we try to make the problem say strong three consistence. And if we do that, we may not ensure that we do not have any backtracking, but the amount of backtracking that we have to do, that may be less. And if we do that, that kind of approach is called path consistency, because we are taking care of a chain of assignments and we are making that to be consistent up to that level. So here we are keeping this CSP to be consistent up to 3 level, for example. Now, let us look at the problem structure a little bit and try to see whether we can design solvers around this. So let us have a closer look at this graph. So what does that graph tell you about the problem structure? Any idea? So while you're trying to assign values to them, and of course the value should be satisfying, the assignment should be satisfying. So does anything strike in you looking at the problem structure? And that relates to assignment of the colors. So let me answer it for you. So you see that Tasmania is isolated from the other part of the network. So I really do not care what assignment I make for the other variables while I am trying to make assignment for T, right? So what does that imply? This implies that if we can subdivide our problem structure or divide our problem structure into sub problems, then we can tackle the sub problems in a more efficient way, right? So basically what we can do, we can divide the problem into independent sub problems, and Then we solve the subproblems individually. And we learned that in algorithm that we have several approaches which takes these kind of techniques into account, divide the problems into subproblems and try to solve the problems individually and come up with the final solution. But the point at this, or the question that at this particular point is relevant, is that how to identify independent subproblems. So what we are doing here, we are having a constant graph and we have to find independent subproblems. So basically what we can do, we can try to see what are the connected components in the graph. So what do you mean by connected components? So if you check this particular subgraph, so this particular subgraph, so here you can see the nodes are connected to each other, but these nodes are not connected to this node, right? So that's why this is a kind of component in the network. And this is another component in the network. Now you see that we can solve this problem individually, right? So we have the techniques to find out the connected component in the graph. So there are algorithms or efficient algorithms to do that, right? So let us see if we do that, what is the benefit? So for this, if we see that we have a problem of having say n variables, then what is the kind of running time if we do not do any decomposition? We know that. So it is in the order of d to the power n, and d is the domain set, domain size. Right? Now let us see if we divide the problems into components, what benefit we'll get. So let's say for the sake of simplicity, we have say divided the whole problem or whole graph into components, and each component is having a size c, right? Then how many components we are having in total? We are having n by c number of components. And if we want to solve individual component, what would be the running time? Can anybody tell me? So what we are having, we have multiple components. We have divided the graph into multiple components, and each component is having c variable, right? So that's why we have n by c number of components. So can you tell me what is the running time for each of these components? Hello? Alapan, can you tell me what would be the answer? So I have already told that if we have a problem of having size n variables, the running time is d to the power n. Now we have a reduced problem size, which is c. Every component is having a size c. We have c variables here, right? And we want to solve this problem individually. So what would be the running time for this to solve this problem?
Like c into d to the power n by c.
C into d to the power n by c. Is it n by c? Why do you say that?
Sir, in the power only n by c will be there.
Yeah, so that's what I have written here. No, just look at my question carefully. I'm asking, we have now divided the problem into subproblems, and each subproblem is of size c. That means it is having c variable. Now, what is the running time to solve these problems? I don't care about how these problems are getting.
D to the power c.
D to the power c, right? So the overall running time, if we consider, so this will also be d to the power c, d to the power c. So overall running time would be order of n by c d to the power c. So do you agree with this?
Yes, sir. I thought it was the other way around. Like there were c divisions. So
Okay. No. Okay. So, yeah. Now, look at this form and tell me whether you have benefited or not. So here we had a kind of exponential sense, right? We are having d to the power n, but here n is appearing in a linear form. So here the running time has become linear because c is a constant to us, right? So that's how we are benefiting, right? So
Sir, I have
the
one doubt.
yeah, sure.
Sir, in this situation, like we can see that the running time has improved very much. Like if we put C to 1, then it is almost order of n into t, so it will be linear. But
Right.
this division also takes some time. So how how is that maintained? Is it too much expensive?
Okay, so let me address your question in a different angle. So I'll come to your question, but the other point is, uh, if you cannot really divide the problem into size 1. If you can do that, then the problem is very trivial. So all the nodes, they are not really connected to each other. So there is no constant imposed on them. So that means the problem is very trivial, right? And the other point is that dividing the problem into sub-problems. So let us take a realistic situation where you have these connected components which are kind of greater than 1, or maybe it is having 5 or 6 nodes, or maybe much larger number of variables. So there is an effort in computing this. I agree with that. So that is a kind of pre-processing that you have to do, right? So that does not come free of cost, right?
Yes, sir.
But if we can do that, and we'll see that it is not always the case we can do that. So what happens if we have something like this? So then you see we cannot do that, right? But the point is, if we can analyze your problem domain and see that these kind of optimizations that you can do, then you should go for this, right?
Yes, sir.
Okay. Now let us take an example scenario where n is say 20, c is n is 80, c is 20, and d is 2. Now without decomposition, we have say to the power 80, and if we can process the nodes like 10 million nodes per second, it will take 4 billion years to solve this problem, right? Now, if we do decomposition, then you see if we process the nodes in the similar rate, like 10 million nodes per second, so we'll be able to solve the problem in 0.4 seconds. But again, with a kind of caution that it is not always possible to divide the problem into sub-problems as we have discussed earlier, and of course, and there is a cost involved in identifying these independent subproblems, right? Now, again, so it is very uncommon to find such a problem. So let me be very candid about that. So let us talk about another kind of situation. So here you see that we are analyzing the problem structure. It is not like that whatever solution I have for a particular structure that will be applicable to other structure. So let me talk about another kind of structure, which is we call a tree structured CSP, right? So you can see here, we do not have, so first thing that you can observe here that we do not have any cycle in this graph, right? Now, if you can say, hold say A node, right? Let us hold this A node and hang this entire structure from top to bottom. So it will become a tree, right? So it will look like this. We have A, then say you have got B, then say C, and B have say D, and D have E and F. So it is a kind of tree structure that we have with us. And we'll see that if we have a tree structure, then we can devise an algorithm which will run in say ND square inverse case. So I guess someone's mic is on. Can you please put off your mic? Yeah. So if we can see that our problem is structured in a tree way, then we can solve this CSP using ND square in worst case. So let us try to see how we can do that. So again, this is a kind of intermediate stage of our CSP. Let us consider that these are the kind of values that are associated with every node. We can do with the full set of colors, but again, for the sake of simplicity, let us assume these colors with us, right? Now we can, what we will be doing first, we will be ordering these nodes in such a way. So this is a tree that we have seen earlier, such a way that the parents of this of each node will precede its children. So let me try to draw it first, then let me explain. So what we have a tree structure like this earlier. So let me go back. So this way. Now from this, I'll first create an edge like this. From B to C, I have something like this. Now from B to D, I have another edge. So something like this. And you see, as a result, we'll be having a structure like this, right? So the first step in the algorithm is that we order the variables in a way that the parents will always precede the children, right? Now, these are the values that are associated with the every node as we have in the example. Now we will try to process the entire structure backward, and we will try to remove inconsistency for the edge, which is kind of parent of xi and the xi itself. So what do we mean by that? So our first node backwards is f, right? So what we will consider? We'll consider the edge from D to F. And we'll try to see whether that is R consistent or not. We know the definition of R consistent. So this is our X and this is our Y, right? So you need to check whether all the values in D are consistent with the values in F, right? So is it consistent? So can how do I make it consistent?
I think remove blue from D.
Okay, so let us remove D blue from D. Now let us check this E and D, because this is the next node in this direction, right? Is this R consistent?
Yes.
This is consistent, so we do not need to do anything. Now let us check for D. So D's parent is B. Let us check B to D. B to D, is it consistent?
Yes, sir.
It is consistent. Then C, B and C, B to C, is it consistent?
No.
No,
How do we
Remove green from B.
Okay, let us remove green from now this node A to B, is it consistent?
no.
I will need to remove.
Of course not. So you need to remove blue from here, right? So our backward pass is done, right? Now we'll be doing a forward pass. In the forward pass, what we'll be doing? We know all the arcs, they have become consistent, right? Now, as the arc, they have all become consistent. I really don't care what assignment I do. Whatever assignment I do for each variable, that will be giving me a consistent solution. So only option that we are left with for A is blue, right? Only option we are left with, so we are doing this pass now, forward pass. For B is blue. Only assignment that you can make for C is green. Now here I can choose any one, right? It can be red or green. I really don't care. So let me use say red here, right? Now here also I can keep anything, right? And then we have, and of course, while we are assigning the child, we need to check whether that is consistent with the assignment that we have made for the parent. So that is one thing that we need to check. So why we are saying this? So let's say we have assigned say green here, right? So up till now, everything is fine. Now here, as soon as I select green for E, then this becomes inconsistent. So then we cannot really assign green here. We should assign blue for this, right? And now if we assign blue, the things are consistent. So you have a solution here, right? So you see the algorithm is super simple. So you just need to order it in the tree order. Then you do a backward pass to remove all the inconsistencies. And as you do it, you have all the arcs to be consistent. And you now try to assign the values to the variables in a forward manner. And one thing that you need to check while you are assigning a value to a variable, you need to check whether that is going well with the assignment that we have made for the its parent, right? So the running time is n(d square). Again, I'll not be explaining it here. You can give it a thought little bit, and you also may like to check out the video that I have shared, and there I have explained why this is n(d square). Now for the tree structured CSPs, so these are the things that we are gaining. So the first gain is that after this backward pass we have done, all the root to leaf arcs are consistent. So this is one thing that we have achieved. And what is the implication of that is that we do not need to do any backtracking, right? Now the proof for this I have discussed in the video, so you can have a look at this. And again, if we have this all arcs to be consistent, the forward assignment while you are doing that will not involve any backtrack, right? But again, life is not that simple. So this works for tree structured graph, but it does not work for graphs that are having cycles. And you need to have a kind of give you the thought why this is not so. And bottom line is that, well, tree structured CSPs, they are very good. But again, as we have talked about dividing the problems into subproblems, that these structured CSPs are not common either, right? Now, one thing that we can do is that convert the tree structured CSPs into or any CSP into tree structured CSP, right? So how do we do that? So what we can do, we can say that we select this node and assign a value forcefully to it. So if we do that, then the values for the respective other connected nodes, they will be reflected, they will be changed. And as we have assigned a value here, we can keep this aside and check the other values, other variables. Now these other variables, they can give you a tree structure. So that is the kind of hope. So what we are trying to do, if we condition this particular variable with a value, then we do not need to worry about it. We just need to worry about the other variables, but these other variables, they will be having their updated domain value. And what you can see that this kind of structure is a tree structure. So though the original constraint graph was not a tree structured CSP, but the updated or the condition, so this is what we call as conditioning. The condition CSP is a tree structured CSP, right? So what do we mean by conditioning then? So what we are doing, we are forcefully instantiating a variable to a value. So let's say I'm saying that I assign green to SA, right? And then prune the other domain values, other values of the domain of the other variables, right? Now that we can do for one individual node, also that we can do for a group of nodes, right? So what is the kind of criteria to do that? The criteria is that whatever set of node that we are selecting to condition the network is that if we remove this set of nodes, then the remaining portion or the residual graph will become a tree. And that is what we call as cut set condition. So what we'll be doing, we'll be selecting a subset of these variables. And if we remove those nodes, the corresponding nodes from the graph, whatever will be left with R3. If we can do that, then we define that to be a cart set. Right. Now, as in the other problem here, also we have a cost involved in identifying this cart set, and there are pretty smart algorithms to do that. Now, the problem boils down to the fact that we have to assign the variables to this, the values to this, and with respect to that, we'll be assigning values to this. Now let's take the simplest case, right, where we have the cart set defined over a single variable, right? Now let us condition our network on this variable. So we select this variable. So the first thing that we need to do is to choose a cart set, and for our network, this is the cart set. Now, this can be assigned green, this can be assigned blue, and this can be red. These three values we can assign, but we do not know for which instantiation we'll be having the solution. So that's why we are taking care of all the contingencies, right? So how many such, if we think about the domain to be D, right? So how many such possibilities will be there if we choose a single variable?
D possibilities.
So we'll be having D number of possibilities. Now let's say if we try to generalize, for every the cart set that we are deciding is of size C, right? So instead of having only one variable, we have a kind of set of nodes, which is our cart set, and the size of this cart set is C. So what would be the size of this particular layer?
D power C.
It will be D power C. All agree with this? So this is why we are doing this. We do not know with which instantiation finally we will be getting the value. So that's why we are taking care of all the contingencies. So though it is exponential to C, but you see this C is a constant. So that's why this is bounded, right? Now for each of these, we will remove this node. As we remove this node, we have a residual tree, right? Now, how to solve this? Now, for tree structure, what is the complexity? The complexity is ND square. So we can solve this by employing any tree structured CSP algorithm, right? That we have decided earlier. Now, to solve a tree structured CSP, the complexity is OND square, right? See, in our case, what is the value of N? Can N of
N minus C.
N minus C. And so the overall complexity will be N minus C D square, and that you have to do for D to the power C. So the overall complexity will be becoming this quantity, right? And again, we have only cost that is involved is this particular layer, right? And of course, this is bounded, right?
Sir, one question on the previous slide.
Okay, sure.
So on that cut set, when you did with one, like the red, green and blue,
right?
At least for this example, aren't the three problems identical? So if you find a solution with red, you will always find it with the other two also?
No, see, these residual problems you're talking about?
I'm saying with the cut set, the first one where you had cut set of one.
Okay.
Aren't the three problems identical?
Which problem you are talking about? This deciding the cart set or assigning the value?
And once you assign a value, whether it is red, green or blue, aren't the three problems identical? And if you find a solution with red, you will always find with the other colors, and vice versa. If you don't find it, you will not find for the others also, no?
That might be possible for a very specific problem, but in other problems you might see that the domains may not be having, for all the variables you may not be having same set of values.
Yeah, the larger cuts.
Hello?
Yes, sir, understood. Yeah.
Okay, good. There is another way to convert a generic constraint graph into a tree structure. So you see, that these graph can be looked in a different way. So we have a substructure like this. We have a substructure like this. And we have a substructure like this. Right. So what we can do, we can define a mega variable for each of these substructure consisting of these small variables. So this is one structure, this is another, and this is other. And we define, so I think, yeah, there is another. So we define a mega variable consisting of all this. And internally what we have the constant that we have said earlier, like WA should not be equal to NT, something like that. Now, what is the benefit that we will be getting here? So now, while we are assigning value, we can treat these problems individually. But one thing that we need to keep in consideration, whatever values that we are assigning to NT and SA for M1, the same value should be assigned to NT and SA in M2, which is a neighbor to this, right? Whatever value that you are assigning to Q and SA in M2, that should be same to values that you are assigning to Q and SA in M3, so on and so forth. So basically, you can define the edges between these nodes. And what does this edge signify? That the common variable, they should agree on values. So basically here we are defining the edges which are imposing new constraints here. So apart from these constraints that we are doing here, we are having new constraint. And as a result, what we are getting, we are having a tree structured CSP. Right? And we know that tree structured CSPs are very easier to solve. And by this way, we can really convert almost all the graph structured CSP into a tree structured CSP. Now, so all the algorithms that we have talked about earlier, they are kind of algorithms that start with empty assignment, right? And then keep on expanding the assignment by choosing one variable, two variable, three variable. But there is another class of algorithms which will start with a complete assignment. And it does not really care whether this complete assignment is violating the constraints or not. It will be just starting with any such assignment, right? But it should be complete. And iteratively try to improve the solution with some heuristics. And that gives us an algorithm which we call as iterative improvement algorithm, right? So basically, it will be assigning the values to change the solution. That's it. And the main crux of this algorithm is that it will not require specialized data structure like stack that we might have to use in the other problems, because there we have a sense of backtracking. But here you will be seeing that we will not be doing much backtracking here, right? So algorithm here again is very simple. So first you have to select a variable which you need to reassign, and you can randomly select any conflicting variable. You don't need to check whether the conflict is huge, conflict is less. You don't need to check anything. Just need to check, select any variable randomly which is having a conflict, right? And then while we are trying to select a value for that we will be selecting a heuristic or using a heuristics, which is what we call as mean conflict heuristics. So we'll be selecting a value that has got minimum conflict with the other assignments. That's it. That's the algorithm, right? And try to reassign values so that we can minimize the conflict, right? So basically, to put the thing in a very simplistic way, so this is the assignment that we have started with, all red to these two nodes, and we pick up one node and try to assign a different value, and that will minimize our conflict, right? Go to a bigger problem. We have this 4-queen problem. We have started with this empty or not empty and a random assignment. And in this assignment, you can see that we have got 5 conflicts. And what we have done, we have moved this queen to upper portion. And here we are removing the conflict by 3. And then we are moving this queen to this place, and we are having no conflict here. And this is a solution, right? Now let us try to do it in a bit generic way. So we are taking 1, 2, 3, 4, 5 queen problem, right? And what we'll be doing, we'll be starting with a solution like this. So we are assigning or placing all the queens in the first column, right? And as we have done that, we see that every node has got conflict to be 4 value. So you can check it, right? Now you can select any one of them, right? Let us select say 4, the first one, right? Now as you select this, we can move it this and this place. And if we move it to these different places, so these are the kind of new conflict values that this queen will be having. So 1, 1, 1, and 1, right? Now, as this all are having the same value, you can select any one from them, right? Now, if you select this position, so we assign the queen here, right? Now, with respect to this, the conflict of the other queens will be revised, right? Because this node or this particular queen is having only 3 conflict, right? Now you can choose any one of them. I can choose 3. I can choose this. I could have chosen these also, right? Now if you choose this, so these are the kind of new conflict values for the cells on which I can move this, right? Now, as this is having minimum, we'll be selecting this particular assignment, right? Now, if you select this assignment, what will happen? We have the revised conflict in the other particular thing. Now, you can see that these might also be revised, that you need to check. We have selected these, and this is having the minimum. And now we have the revised. And we can select this. Now, as you select this, we have the solution, right? Now, this mean conflict or this iterative improvement algorithm is a better way than the other algorithms that we have talked about. And this works in a different way than the algorithms which start with, say, empty assignment. So here we start with a complete assignment and then go on refining the solution. So again, I'm not going for the demo. You can have a look at it. Right. Now, I think I have, okay, let me first tell something about this performance of this mean conflict heuristic. And it will see that this is a kind of huge improvement that we can get in respect to solvability of the n-queen. So the point is, it can solve n-queen problem for arbitrary n, like so. You see this number. So earlier, with all the heuristics and other things, we solved, say, n-queen problem up to 1,000. Right now, here you can see that we can solve this problem with high probability in a constant time. Now, there is a kind of experiment that was done using random CSPs. And there was a quantity ratio, which is the ratio between the constant size of the constant set and the size of the variable set. Now, if we plot this ratio and the CPU time, you will get a curve like this. What does that mean? So if you have a very low ratio like this region, the problem can be solved in a pretty faster manner. And also, if you have high ratio, you can also solve the problem in a very faster way. But there is a region, very small region, where which we call as the critical ratio. There we might get a situation where we might not have a solution for the CSP, or even if we have a solution for the CSP, it might take huge amount of time. But this is a very narrow region. If you are very unlucky enough, you will get into this region. And that's why we are talking about this can solve this n-queen problem or of arbitrary value of n with high probability. So if you are into this region, you may end up with getting no solution, but for the other, you will be getting solution in a pretty faster manner. So again, it gains a lot. So you can see in n-queens, it has reduced from 817 to 4K comparisons. Right. So let me try to summarize the CSP module. So this CSP is a special instance of the search problem, and we are trying to go for a generic algorithm to solve the problems. And the baseline algorithm is backtracking, which is basically equivalent to uninformed search for CSP. And to speed up this backtracking, we can use different ordering, filtering, heuristics, and also we can look at the problem structure. And finally, we have seen this iterative mean conflict is a more practical CSP algorithm one can work on. Right. So at this point, I think I'm done with CSP. If there are any questions or doubts on this, I'll be happy to take. Otherwise, we can take a quick break for 5 minutes and then proceed with the next part, which is the satisfiability problem. So, any questions?
Sir, I have a doubt.
Yeah, sure.
Can you explain the main conflict heuristic with respect to the 5 queens problem, how the algorithm is working?
Okay, okay. So what we do, so our objective is to place the queens in every column so that they are not attacking each other, right, Nilanjan?
Yes, sir.
Now we start with a complete assignment. So we are allocating the queen or placing the queens in every row of the first column. So you are okay with that?
Yes.
Now for every assignment, we compute the number of conflicts. So for this, how many conflicts we are having? We are having 4 conflicts, right? For this, we are having 4 conflicts, and for every such assignment, we are having 4 conflicts, right? Now,
Yes.
we will be picking up a variable which is conflicting. I really do not care whether the conflict is minimum or not, or maximum or not. I'll pick up any. I could have picked up this. I could have picked up this. Anyone, right? So in this example, we have picked up this this one, right? Now, as we have picked this up, so what we can do, I can place this in one of the columns in this row, right? Now I'm computing a contingency. If we place this into these cells, what would be the expected conflict? So if I place it here, the conflict is 1. If I place it here, the conflict is 1. If I place it here, the conflict is 1. And if I place it here, the conflict is again 1, right? Now, as all the values are, so these are your age values, right? All the age values are same. So that means I can place it anywhere, right? I have placed it here randomly. Now, as I have placed it here, now you check for this. Now this is having how many conflicts? So this is no longer having conflict with this queen, but it is having conflict with the other. So that's why this is having the revised conflict value to be 3. It is having conflict 4 because it is having conflict with this again, right? So, but the others, they are not having conflict with this assignment. So that's why their conflict value is 3, right? Now we have placed it. Now we have to select another variable. I could have selected anyone. So in this example, I have selected this, right? Now, as I have selected this, I have to compute the contingency to place this in different cells in that particular row. And if we do that, so these are the kind of conflicts that I'm having. So if I place this here, I have 2 conflicts with this and this. I have placed it, if I place it here, I have 2 conflicts with this and this. If I place it here, I am having 2 conflicts with this and with this. Right?
Yes,
Sorry, not with this and this, sorry. And if we place it here, I have 0 conflict. So here I have a minimum. So I'll be selecting this, right? So if I select this, my conflicts for the other variables, they are revised, right? Now I can select anyone from this. So if I select this, again, I'll be computing the contingency, and this is the minimum. I can place the queen here. If I place the queen here, I have the revised conflict values or age values. And with this, I can select. So here I've selected um, queen that is having higher H value. So that does not really matter. As long as a variable is having conflict, I can select that. Right. Now, as I have selected these are the contingencies. So this is minimum. I'll place it here. And then finally, this is having zero conflict. So I can place it here. So this is my solution.
So, sir, we are always selecting a value which has some conflict, not necessarily the minimum, and then moving it to a position which has the minimum conflict.
Exactly. Exactly.
So, sir, in that case, we could have also selected the one which we had removed, which we had moved in the first place. We could have also selected that in some.
Yeah. So what we'll be doing, so this is a kind of heuristics. As long as I do not have conflict with the others, so they are having zero conflict. So no, so I could have selected this in this case. That's fine, but yeah, so that we could have done because that is having a conflict. But here, as we have seen that this is having zero conflict, I should not disturb this solution.
So, sir, in this case, what we are doing, we are if we are collecting all those variables which have some amount of conflict, and then irrespective of the number of conflicts, we are randomly choosing anyone.
Right.
So, sir, if we do it in this case, that in this way, that we are every time choosing the variable with already minimum conflict, so will not it improve the algorithm?
I think that will not have any effect in the runtime. And additionally, what it will do, it will impose a burden of sorting this heuristics value. But that will not have any effect in the solution at the end.
Okay, sir.
Okay, so we are done with this CSP. So so we can have a quick break, maybe it's already 9:35. So let us meet at 9:40. At least we can start the introduction part of satisfiability.
Kati?
Hello, is the first slide on satisfiability problems is visible?
Yes, it is.
So I think let us get started with. I hope you know George Boole, right? By whose name this Boolean logic is famous, and this is what happens when Boole orders for a lunch. So you see, there are so many yes and no's, and finally, whatever the assignments George Boole makes, you have to come up with a satisfying lunch menu, right? So let us talk about satisfiability problems, and satisfiability problem we'll look at something similar to that, where you have got different variables and in a formula, of course. And finally, your objective is to find out an assignment of the variables for which you'll be declaring this formula to be satisfiable, right? So the finally, the outcome, either there might be an assignment for which your formula is satisfiable, or you might not be having any assignment for which the formula is satisfiable. In that case, we'll declare that formula to be unsatisfiable. Right. I think these are the kind of concepts that are involved in this particular problem of satisfiability. So this particular part where the problem encoding part is concerned, which we have already talked about in our logic course, because the satisfiability problem, they are really applicable over propositional formula, and we know how to devise propositional formula, and we know that there are different algorithms or inference algorithms by which infer new knowledge given a propositional knowledge base. And basically we come up with a Boolean formula, and we want to declare whether that formula is satisfiable or unsatisfiable. So our primary focus would be on this, to devise these complete algorithms, and by complete means whenever we have a solution or we have an assignment for which the formula is satisfiable, we'll be able to come up with that particular assignment, right? And another version of these algorithms are called incomplete algorithms. So they might sometimes fail to provide answers, even though the answers are there, but they might give you the answers in a pretty quick manner than maybe complete algorithms. So under complete algorithms, we'll be talking about like DP algorithm that uses directed resolution, basically the resolution rule that we have discussed in the logic module. And we'll be talking about an advanced version of this DP algorithm, which is DPLL algorithm, which makes use of a specific form of resolution, which we call as unit resolution. And we will try to optimize DPLL further by doing smart ways of backtracking to the points after we get a failure, right? So basically, these solvers, they can be looked at in different ways. So the CSP solvers can be looked at as an inference satisfiability problem, which we call in short as SAT. So we can treat SAT solver or design SAT solver by inference, or we can design SAT solvers using search techniques. And we'll see that we have similarity of this approach with CSP approach that we have just discussed. And finally, we can combine these both, inference plus search. Basically, this DP algorithm belong to this inference domain. This DPLL algorithm belong to this search domain, and DPLL plus belong to this inference plus search domain. So these are the primary three things we'll be talking about in this particular module. So let us focus on the why and what part first. So maybe I'll talk about what part and then go to why. So you understand what is propositional logic. Just to recap the ideas, we know that a literal is a Boolean variable or its negation. So a literal can be in its positive form like x, and x bar, which is the negative form. And we define a clause to be disjunction of literals. For example, I can have a clause like, say, x1, x2, or x3 bar, something like that. So this is a clause, and these are all connected by disjunction. And finally, a CNF formula, conjunctive normal form formula, is a conjunction of different clauses. So this is an example where we have got three clauses. So we have these three clauses, and the variables involved in these clauses are x1, x2, x3, and literals are x1, x2, x2 bar, x3, and I guess x3 bar, right? So basically, you have three variables, but you might have, say, 3 multiplied 2, that is 6 possible literals, both in positive and taking care of the negative and the positive form of the variable, right? So our main focus would be to prove the satisfiability of a CNF formula. So let us try to see what we mean by that. So whenever we talk about satisfiability, we need to talk about truth assignment. So truth assignment is what is a function. So what does it do? It takes a variable as input and assigns either true or false. So this is the this is what this function truth assignment does, right? Now this assignment will satisfy x if we can assign phi x to be true, or it will satisfy x bar if we assign phi x to be false, right? So if we assign x to be false, so that means this literal will become true, and if we assign x to be true, this entire literal will become true, right? Now, when do we say that our clause is satisfiable? Our clause, like again, I'm writing, say x1, x2, x3. So this is satisfiable if at least one of the literals is true. So if at least one of them is true, the entire clause will become true. Now, when a CNF formula is true, what assignment makes a CNF formula true? If it satisfies all the clauses. So let's say we have a clause like say x1, x2, x3, and say x4, x5, x6, right? So in order that this CNF is satisfied, we have to have a phi that assigns value to x1, x2, x3, x4, x5, and x6 such that each of these clause is satisfied, right? Now, how will each of these clauses be satisfied? So so at least one of the literals, they become satisfied in each of these clauses, right? Then only each of these clauses will be satisfied, and if every clause is satisfiable, then your CNF formula will be satisfiable. So we say that a phi is a satisfying assignment. So phi is again what? Phi is basically it is assigning values to the variables xi, right? Either true or false, right? Now we say that this phi is a satisfying assignment if mm, for this particular CNF formula f, if this assignment satisfies f. So that means this formula f evaluates to be true for an assignment phi, right? So when do we say that our formula f is satisfiable? If we can find at least one assignment that satisfies f, then only we can say that f is satisfiable. So it may be it may not be satisfiable by another assignment, but we can find at least one assignment for which f can be made true. Now, how do we define a satisfiability problem? So as input, it takes a formula f and try to see whether this is satisfiable or not. And how to do that? How to check that? We need to come up with at least one assignment such that f evaluates to be true. So this is the whole description of the satisfiability problem, right? Let us take a quick look at some examples of formulas that are satisfiable and some formulas that are unsatisfiable. So this formula is satisfiable, of course. I can assign x1 to be true. This formula becomes satisfiable, but this formula, I guess I have to put 1 here. So this formula is unsatisfiable. Whatever value you put or assign to x, whatever assignment that you can make. So for example, if you make say x1 equal to t, then this will become unsatisfiable. And also if you can make this to be false, this will again become unsatisfiable. How about this? The first one here. So this of course should be satisfiable. The second one, it again should be satisfiable. The third one, you can take a look at it and you see that it will become unsatisfiable. And finally, this will become unsatisfiable. Right? You cannot have any assignment for this variables for which you can have a satisfaction value or truth value. True value. Let us take a real life example, and this example concerns scheduling a meeting, and this meeting involves 4 persons, and here is a set of constraints that are imposed by these persons. So A says that A can meet only on Monday and Wednesday, B says that he or she cannot meet on Wednesday, C cannot meet on Friday, and D can meet only on Thursday and Friday. The question is whether we can have a meeting or not, right? So the other constraint are that there cannot be more than one. They can meet only once in a week. And so how do we model this as a satisfiability problem, right? So if we define the variables to be like so say x1. So let us define x1 to be we can have meeting on say Monday. And say x2 can have meeting on Tuesday. and so forth, right? Now, how do we represent that A cannot meet on Monday and Wednesday? So if A can meet only on Monday and Wednesday. So if we study this fact or statement, then I do not see this thing. So I just see this and say that there can be a meeting on either Monday or Wednesday. So how do we represent that? We can say that X1 or X2. So this is true, right? And how do we represent that B cannot meet on Wednesday? So that means there cannot be a meeting on Wednesday. How do we represent that? We can represent that to be no, X2 is not Wednesday. So X3 is Wednesday. So you cannot have a meeting on Wednesday. So X3 is not possible. So this is the way we can define the propositions, right, or clauses. Finally, we can define this as a SAT problem by saying that this clause is true. So this represents the first statement. This represents the second statement. This represents the third statement. And this represents the fourth statement, right? And the other constraint says that there can be at most one meeting, right? And this again is not in a kind of propositional form. We can make it in a propositional form by rewriting this like say x1 bar or x2 bar. So you just have to have a closer look at it. I think similar thing we have discussed in other problems, right? So now what we have got the formulation in our CNF. Right. So all the clauses inside, they are in disjunction form, and the clauses are connected via these conjunctions. Right. Now this, so this is our F. Now if we put F into our SAT solver, that SAT solver will either output SAT or unsat. And in this case, this is unsatisfiable. This is proven to be unsatisfiable. Now, SAT is a kind of hard problem to solve. So SAT belongs to this NP complete category in problem class. And the kind of consequence for that is that there is no polynomial time algorithm for SAT. And whatever known complete algorithms that we can think of, their runtime is exponential in worst case. But again, we should be a bit optimistic to find out some tricks to solve the problem in a faster manner. And that is what we will be talking about in this particular module. Now let us look at the why part of it. So what are the applications of SAT? SAT is widely used in hardware model checking. So for example, our chip has been designed, so for example, by Intel, and we need to see whether the chip is performing the functions that it is intended to do. So that means there is a specification before we start designing this chip. And finally, you have to carry out a rigorous test whether the kind of behavior that it has to produce, whether it is producing or not. And how do you do that? You can encode this behavior into form of this propositional formula in CNF and feed that into your model of the chip and try to find out whether that will be satisfied or not, right? And similarly, you can use it to check whether a particular design service is kind of exhibiting its intended behavior or not. And this is widely used in industry. As it is used in hardware model checking, it is also used in software verifications. For example, many of the Microsoft products, they are used in, they are verified using this SMT solver, which is what we call a SAT modulo theory solver, right? And in say cars, aeroplanes, there are various embedded software. So there are very specific devices in which different softwares are running. And you know, these applications are very safety critical applications, right? And they should be verified to its greatest extent. And that is being done quite successfully using these SAT solvers, And for planning and scheduling problem, the SAT is yet proven to be one of the best approaches, right? I think there in the planning module, we'll be talking about an approach of planning that uses the SAT algorithm, right? And the SAT is used in number theoretic problem. One such problem we'll be discussing, I think, in one of the coming slides. And finally, it has got a very close connection with NP-hard problem. So let's say you come up with a problem statement and you suspect that this belongs to the NP-hard problem domain. So the best way to prove that, you try to prove that this problem is equivalent to SAT problem, and people will believe your statement that your defined problem is an NP-hard problem, right? So with this, let us talk about SAT encoding. In the first problem that we'll be picking up for the SAT encoding is a number theoretic problem. And this particular problem concerns the Pythagorean triple problem. And you know Pythagorean triples, right? So if you have a relationship between these three triples, say a squared plus b squared equal to c squared, then we say that ABC is a Pythagorean triple. Now, the particular problem that we are interested in is that, let's say we have the set of integers. Now, can we partition this set of integers into two sets so such that none of these sets contain a Pythagorean triple? So what we are doing? We are dividing this set of integers into two sets. And you know, if we consider this set of integers as a whole, we can find out Pythagorean triple like say 3, 4, 5. This is a Pythagorean triple, right? Now you divide the integer set in two sets, say S1 and S2. And let's say you assign 3 and 4 in set 1, and you allocate 5 in set 2. And if you do that in this way, you cannot have a Pythagorean triple here in S1, and you cannot have a Pythagorean triple in S2. The problem is whether we can do that, right? Another variation of this problem is that, so let's say we have a Pythagorean triple a square plus b square equal to c square. Now we want to assign colors to the individual elements in this triple. So I can either use say red or blue color. These are the two colors I can assign to this entries in this triple, right? Now we should.
So Plavan,
Yeah.
Sorry to interrupt. I think it is time today.
Okay, sorry, I went out with flow. Yeah, sorry, thank you. I think, yeah, we can resume this in the coming half. Okay, yeah, thank you for reminding. So anyway, so any questions at this point?
Sir, can you once move to the slide where you gave some examples of the propositional logic, the set form of propositional logic?
Okay, so those who are done may leave, or those who are having questions may stay back. So yeah. So this is the slide you're talking about?
Yes, sir. Here, the last formula, why is it unsatisfiable? Like if we assign x1 to be true and x2 to be false, then is it not satisfying?
X1 to be true and X2 to be false. Okay. So first one becomes true. The second one becomes true. Yeah, so it is satisfiable, right? So I think I thought of something else. Maybe the connectives they messed up. Yeah, I think it will belong to satisfiable, right? Thank you. Yeah. So, okay, so if there are any other questions, we can take it up in the next hub. Yeah, I think we are done for today. Shurash, I think you can stop the recording.